everyone. I'm Shifty Adhikari. So today is the week 5 of the Discrete Mathematics course. This is NPTEL course Discrete Mathematics. So first I will discuss about this problem 7 and problem 8. Problem 7 and problem 15 in week 4. So I skipped these problems because I had some problem with proving these theorems. Proving these results. So today I will first prove this. Solve this problem 7 from last week, and then we will move forward to today's topics. So in the last week we had this problem that R1 R2 are given to equivalence relations on an ORMP set X, and then we have to prove or disprove this statement that this R1 union R2, this is also an equivalence relation if and only R1 composition R2 is equals to R1 union R2. So basically what we have to prove here is that R1 union R2 is equivalence relation, or ER in short, if and only if R1 composition R2 is equals to R1 union R2. So this is what I have to prove. So first we will put this direction that let us consider that this R1 composition R2 equals to R1 union R2, and we have to prove that this R1 union R2 is equivalence relation. Now to prove that this is an equivalence relation, there are three cases. So there are three properties that we have to prove. First property is reflexive property. So what was the reflexive property? That for any A belongs to X, we have to prove that AA also belongs to R1 union R2. Then on only we can say that this is a reflexive relation. Now is that true or not? So if A belongs to X, so if A belongs to X, then we can definitely say that AA belongs to R1. And that would imply that this is a subset of R1 union R2. So that implies that this AA belongs to R1 union R2. Second, we have to prove the symmetric relation. So what was the symmetric relation? That given AB belongs to R1 union R2 and BC belongs to R1 union R2, we have to prove that AC also belongs to R1 union R2. Now to prove this, there are three cases. So the first case is that if AB and BC both belongs to R1 or they both belongs to R2. So any one of them. So if this is true, so let's say that both of them belongs to R1, and the for case R2, the thing on the group will be same. So if they both belongs to R1, then we can say that AC also belongs to R1. Since R1 is a equivalence relation and both of them belongs to R1, this will imply this because R1 is a transitive relation. Now the third case was uh, so that is case 1, and for case 2 we had we have that AB belongs to R1 and BC belongs to R2. So basically, both of these AB and BC they belongs to two different relations, R1 and R2. So what about now? We know that this. So our condition was that R1 and composition R2 is equals to R1 union R2. So now, if this belongs to R1 and this belongs to R2, then we can see that this. So this is the case that R1 composition R2 is look like this. So first we are using this R2 and then we are using this R1. So basically this will imply from here we can say that BA belongs to R1 and CB belongs to R2. Since R1 and R2 both are symmetric relations. And from there this will imply that CA this belongs to R1 compose R2 because CB. So the CB is basically in R2, that means the C is related to this B and B is also related to A, and since R1 composition R2 is equal to, so basically we can say that this CA this belongs to R1 composition R2 and this is nothing but R1 union R2 according to the hypothesis of R. And so we can conclude that AC belongs to this R1 union R2. Because as we have proved that this R1 union R2 is already a symmetric relation. Oh, sorry. Symmetric, this is a transitive property. This is the symmetric, this is our transitive. So we have proved the transitive property of R1 union R2. The reflexive property is easy to see for R1 union R2, and also symmetric property is also easy to see for R1 union R2. Now the non-trivial part was this transitive property. So for these two cases, we have proved that this is indeed a transitive relation. And if we consider another case, which is basically this BC belongs to R1 and AB belongs to R2, then for that we can directly say that this belongs to R1 composition R2 and which will be a subset, which will be equal to R1 union R2. So that means we can say that this deduction is true. That means if we consider that R1 composition R2 is equal to R1 union R2, then that will imply that R1 union R2 is a equivalence relation. And the second part was that we have to consider that this is equivalence relation, and from there we have to prove that R1 union R2 is actually equal to R1 compose R2. Now for this part, what we have to do is that R1 union R2 is a subset of R1 compose R2. That's the first thing that we have to prove. So to prove this, we can take a random pair AB in R1 union R2. Now since AB belongs to R1 union R2, we can consider without loss of generality that this AB belongs to R1. Now the relation map was like this. So from X first, so R1 composition R2 is basically first we have this R2 map, sorry, this R2 relation, and then we have this R1 relation. Now we have AB belongs to R1, and also we know that this A belongs to R2. Since R2 was an equivalence relation, then it is also a reflexive relation. So we can say that AA belongs to R2. Now AA belongs to R2 and AB belongs to R1. Both of them would imply that AB belongs to R1 compose R2. So that means that we have taken a random element from R1 union R2 and we have proved that that arbitrary element, uh, this belongs to R1 composition R2. So this part is proved. And the second part is that we have to prove that R1 compose R2. This is a subset of R1 union R2. Similarly, we just consider an arbitrary element AB in R1 compose R2. So if this belongs to R1 compose R2, then what we can say is that there exists a C in X such that AC belongs to R2 and CB, this belongs to R1. This is how this R1 composition R2 is defined. Now AC belongs to R2, so that means that this also belongs to R1 union R2. And CB belongs to R1, that means it also belongs to R1 union. Now, since R1 union R2 is an equivalence relation, which was already given us because of this hypothesis, so we have considered this hypothesis, now we have to conclude this one. So we are given this hypothesis that R1 union R2 is already an equivalence relation. So therefore, we can say that R1 union R2 is a transitive relation, and from there we can conclude that this AB belongs to R1 union R2. So that means this relation is also true, and therefore this is true. Now, in last week we had also skipped. I forgot to include or the proof these statements also. So I will put this here and then we will move to the next today's assignment. Okay, so first of all, we have this statement that every non-empty symmetric and transitive relation is also a reflexive relation. So we have to prove or disprove it. So if we want to disprove this statement, then basically we have to give a example for this. So let's consider that example. So consider the X set AB, and on this X set, we consider our relation like this, which is AA, AB, BA. Now we consider the matrix corresponding to this relation, so that will be basically like this. So corresponding to A and B. So AA is there, AB is there, and BA is also there, but BB is not there. So this is the relationship matrix. And the question is, so the statement was that every non-empty symmetric and transitive relation is also a reflexive relation. Now, is this symmetric? So if we consider this AB, so AB belongs to this relation. So if AB belongs to a relation, so it's a symmetric. Condition for symmetric was that if AB belongs to the relation R, then BA should also be, that will imply that BA also belongs to the relation R. Now AB is in this relation, and BA is also in the relation. Similarly, A is also in the relation, and A in the relation, then AA is in the belongs to this relation. This will also be true. So this is symmetric relation. This relation. So this is definitely a symmetric relation. Now, what about the transitivity? Now, for transitivity, what we have to see is that for any pair A, B, and BC, that is in this relation R, AC must also belong to R. That is, the transitive relation was that for AB and BC in the relation R, so both of these pairs are in the relation. That will imply that AC must also belong to the relation R. So this was the condition for transitive relation. As you can see here, that AA belongs to this relation. Now BA is also in this relation. So that means AA should also be in the relation, and that is true. Now consider this pair AB. Now the AB is in the relation, BA is also in the relation, and that should imply that AA should be in the relation, and that is also true. Now, so we can see that the transitivity property holds for this three elements in this relation. So this is also transitive and symmetric. But what about the reflexive property? So the reflexive property says that for all A in X, AA, this pair, must be in the relation R. But as you can see, B belongs to this set X, but BB does not belong to this relation. We have given an example for which this statement does not apply. So this is not true, or we have just disproved this. Okay. So the second statement is that if g of f is an injective function, then f is also an injective function. And if and g are given a mapping from A to B and B to C respectively. So if is given as a mapping, okay. So there are three sets A, B, and C. From A to B we have the mapping F, and from B to C we have the mapping G. So now the question is that if g of f, or basically G composition F, this is an injective function, then we have to prove that F is also an injective function, or we have to disprove that. So basically we will try to prove it here. So we will prove it by contradiction. So we consider that this statement is true, that f is an injective function, and this statement is false. And we will arrive at a contradiction. So assume if is not injective, and G compose F is injective. Okay. So if is not an injective function, what does that mean? That means that, so what was the definition of injective function? So if we consider two different elements in the domain set, then they should map to distinct elements in the codomain set. That was the definition of injective functions. So now if we say that this function f is not injective, what does that mean? That means that we can find at least one pair in the domain set such that they both map to the same element in the codomain set. Okay. So basically what we can say is that, so there exists A1 and A2 in A, the set A, the domain set for the function f, such that this A1 is not equals to A2 and f of A1 is equals to f of A2. So if it is not injective, then we can arrive at this conclusion. And if this is true, then now what is f of A1? So G compose F1, that should be G of f of A1. And similarly, G of f of A2. Now, what we have seen here is that f of A1 and f of A2, these two are equal. And we consider that to be, let's say, some element B in this codomain set B. So B belongs to B. So now, over here, what we can say is that this is nothing but equals to G of P, and this is also equal to G of P. Now, since G is a mapping, then obviously if there is an element B like this over here, then B should always be mapping to a single element. I mean, there is only a single element in the codomain set, which is uh, where this B maps. It cannot be possible that B maps to two different elements in the codomain set. It is not possible. That violates the definition of the mapping. And therefore, we can say that this G of B and so basically this GOF of A1 and GOF of A2, both are same. A1 is equals to GOF of A2, where this A1 is not equals to A2 because that's what we had assumed over here. This A1 and A2 are two distinct elements in the domain set A. So now, so basically we have two different A1 and A2 in the domain set A such that this GOF function, sorry, this decomposition F function maps to the same element. So that means this is not an injective function. That is a contradiction because we have assumed that if it is not an injective function and GOF is an injective function. So this GOF is is not an injective function. This is a contradiction. Therefore, our assumption was wrong. That is, we have to this if is indeed an injective function. Okay. So we have proved it by contradiction that if this is an injective function, which is decomposition if, then if must also be an injective function. Okay. So now the third statement is that if GOF is an injective function and G is also an injective function, then here if an G are two functions, and so if GOF is an injective function, then G also must be an injective function. So we will give an example where we will see that this is not true. So the GOF function maps like this. We have A, we have B, and we have C. First we have F, and then we have the function G. So we can take an example. So let us consider this example that we have 1, 2 over here, and we have 1, 2, 3, 4, and over here we have again have 1. Okay. So now 1 is mapping to 2, 2 is mapping to 3, 2 is mapping to 2, and 3 is mapping to 1. So we have a mapping like this. So this is our mapping F and this is our mapping G. And as you can see here that this GOF function is a mapping from this set A to this set C, and the mapping is something like this. So GOF mapping would be, so let me draw the GOF mapping. So the GOF mapping is from 1 to 1 to, and 1 would first map to 2 and 2 would map to 2. So 1 would be mapping to 2, 2 is mapping to 3, and 3 is again mapping to 1. So 2 would be mapping to 1. So this is our GOF function. And indeed GOF is an injective function. But as we can see, the G function is not an injective function because 1, 3, both of these are mapping to 1, and 2, 4 is mapping, both of them are mapping to 2. So GOF is not injective. So we have given an example where this is not true. Now finally we have if GOF is a surjection, then F is also a surjection. So we will disprove this also. This is not necessarily true. So again, we will give an example. So in this example, what we will have is, so basically, so we can use the same example. As we can see here, that GOF is a mapping from this set 1 to 2, 1 to, And this is definitely a surjection, because for each element in this set C, we consider this A, consider this C. So this is our A, this is our B, and this is our C. So if we consider this any element in this set C, then for that element there is a P image for this function G composite in thing. So definitely G is a surjective. Now, what about the function f? Now, as you can see that if this 1 is mapping to 2 and 2 is mapping to 3, but for 1 in this codomain set of this f, for 1 in B, there is no P image. So there is no element assigned to this element 1. So therefore, f is not surjective. Sorry, f is not surjective. So in the same example, we have shown that this is not necessarily true. Okay. So now let's move to the assignment problems that we have for week 4. So in this problems, we have the so in this over here we have 4 statements, and we have to uh, see whether the statements are true or not. So first said that the Hisse diagram will always contain at most one maximal element and at most one minimal element. So we know that if we consider this partial order set, Z is equals to, where Z is basically the set of all integers, and this means that the natural ordering among the integers. So if we consider the Hesse diagram, so that will be like this. So let's say we have 0 over here, -1, -2, -3, and will not solve. And similarly, we will have 1, 2, and it will also not stop. So basically, in this ordering, we cannot have a maximal element nor a minimal element. So it is true that uh, there, it is possible that in the Hisse diagram there is no maximal element or a minimum. So that is possible. And what about one maximal element? So as we know that if we consider the all the we consider only a finite set. So let's say uh, we can consider this set 1, 2, 3 with the natural ordering of integers. So if we consider this, then this is again a two set, and the ordering should be like this. The Hisse diagram is basically like this. And in this case also there is one minimal element and one maximal element. But the statement that we are given is that there exists at most one maximal element and one minimal element. So is this true or not? So let us consider an example. So an example should be, so let us consider a set uh, 1, 2, 3, 4 up to 10. So the first 10 in natural numbers. And the ordering should be, so basically we can say that A, P belongs to the relation R such that if A divides B, so we consider a relation like this R. And we have seen in the lectures that this is a coset. We can consider this set X. So this XR, this is a coset. And what is the Hisse diagram of this coset? Okay, so instead of 1, so we will basically take this set from 2 to up to 10. So now the Hisse diagram will be like this: 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So this is the histogram for this partial order circuit. Okay. So basically, 2 divides 4 and 4 divides 8. And similarly, 6 is divisible by 2 and 3 both. So we have created the histogram. And as you can see, so what are the minimal elements? So minimal element means that there is no other element which is so so basically we can call A to be a minimal element, not minimum but minimal. Whenever we can say that there exists no element B such that B is less equals to R. So this is basically the relation R. Okay, basically B related to R, and B is related to R whenever B divides C. So that means that in this case we can say that A to be a minimal element when there exists no divisors of it. Then only we can say that A is a minimum element. And over here, since we are considering all the elements from starting from 2, therefore all the prime numbers 2, 3, 5, 7, these are our minimal elements. So there are 4 minimal elements. And what about the maximal elements? The maximal elements are basically all those elements in this set that does not divide any elements in this set. So considering 8, 6, 9 and 10, so these are the maximal elements which will not divide any other element in the set. I'm considering this relation R, which is defined over here. That means A divides B. AB is related whenever A divides B. So according to this relation, the maximal element should be all those elements that does not divide any other elements. Okay. So there are 4 minimal elements and 4 maximal elements. So therefore, this statement is not true. That means his diagram must not contain at most one maximal and at most one minimal element. But rather, the actual statement should be at most one maximum element and at most one minimum element. Now remember that there is a difference between this maximal and maximum, and similarly minimal and minimum. Being maximum or minimum means that so being maximum means that it is greater than all other elements in the space, and also being minimum meaning that it is less than all other elements in the space. So the first one is not true. So what about this? So we are given a relation on Z saying that A and B are related if AB plus 13B is congruent to 0 or 7. Okay. So we are given that AB is so this AB is in the relation if 4A plus 13 is congruent to 0 or 70. Now, what does that this mean? That 4A plus 13B is congruent to 0. That means that if we divide this value 4A plus 13B by 17, the remainder should be 0. This is the meaning of the statement. So that means we can write this like this for some k in the for some integer k. So now we have to consider we have to prove that this R is an equivalent relation. So for proving that, we have to prove the reflexive property, the symmetric property, and the transitive property. So first we prove the reflexive property. If we consider any A in Z, then we can say that 4A plus 13A is definitely equals to 17A, which is nothing but congruent to 0 mod 17, because if we divide this value by 70, then definitely the remainder would be 0 because it is a multiple of 70 for a integer a for integer a. Okay. So that means we can say that a belongs to the relation R. Now what about the symmetric relation? Now for symmetric relation, what we have to prove is that if AB belongs to the relation R and B, oh sorry, if AB belongs to the relation R, then we have to prove that BA also belongs to the relation R. Now if AB belongs to R, then for that we can write this directly, that this 4A plus 13B is nothing but a multiple of 70. Now 4A plus 13B is a multiple of 17. We can write this as 17 minus 13A plus 17 minus 4B. So that means we can write it as 17A plus B minus K should be equal to 13A plus 4B. If we simplify this, then we will get this equation. Okay, so that means we can say that this 13A plus 4B, or rather 4A plus 13B, is basically a multiple of 17. Because this A, B, K, all these are integers. So therefore, this we can say that this is nothing but a multiple of 70. And that means this is nothing but concurrent to 0 and 70. And oh, sorry, this is 4B plus 13. This one. Therefore, we can write that BK belongs to R, the relation R. So we have assumed that AB belongs to R, we have proved that A belongs to R. So definitely, this is a symmetric relation. Now the final is, finally we have to look at the transitivity property. So to prove the transitive property, what we can do is that we can assume that AB belongs to R and BC belongs to R. Now if AB and BC both belongs to R, then from this relation from here, we can say that 4A plus 13B is a multiple of 17, and also 4B plus 13C, that is also a multiple of 17. So instead of K, we can write it as some M, where this K, M both belongs to some C. So basically this K and M are some integers. So we can write this. Now we can add this together and we can get that 4A plus 13B plus 4B plus 13C is 17K plus M. And this is nothing but, we can write this as this 17K plus M minus B, because this will be nothing but 17B, and we can take this to the right hand side and we will get this equation. This K, M, B all are integers, and therefore we can write that, we can say that this is divisible by 17, that is this is 0 17. This implies that AC, the pair AC, this also comes to the relation R. So now we have seen that this is true, that this relation R, which is defined by this is indeed a equivalence relation. Now the third question is that the inverse of function f is defined if f is both injective and surjective. Now we know that f is both injective and surjective. That means that, so f is injective and f is surjective. That will imply that if sorry, that will imply that it is a bijection. Now what do we mean by inverse of a function? So inverse of a function means that if we take any a from the set X, and if we compute, so let's say that this F inverse is denotes the inverse of the function. Then if A is any element, then F inverse of F should be for all A in the domain set of X, or the domain set of F. We take any A from the domain set of F, then that should give us this. That is F inverse of F is equal to A. And the question is that, can we say that if F is a injective and surjective, then there exists an inverse? So basically we can say that. So how do we define that function? So here the F function is given as an injective and surjective function. So that if for all, so consider this is function from A to B. For all B in this B, there exists a such that f of A is equal to B. Now we define F inverse of B as A. So now the question is that is this F inverse function is well defined or not? So that means that is it possible that for one single element over here there exists two different mapping of F inverse? F inverse mapping is mapping to two different elements in this domain set of F. Is this possible? So that is not possible. Why? Because F itself was an injective function. Because for two different mapping over here, for two different elements in the domain set, it was mapping to two distinct elements in the codomain set. So if we consider any element over here in the domain set, then and if we reverse it, if we traverse back to the codomain set, then that would be a unique element that was assigned to this element B. Now, what about the criteria for surjective? Can we say that this is defined for all B? This is also defined for all B because, as we know, that this F function is surjective function. So for all B, we can find such a range of F. That means we can define this F inverse of F. And so, what can we say about F inverse of FB? F inverse of F. So if A will basically map, so if we consider any A over here, F will map to an element B over here. Now B should, F inverse would basically take it back to A, that unique element that was assigned to this element B over here. So this is indeed here. So if F is a bijection, then we can definitely define a inverse function for that bijective function F. So this is also true. And what about the final one? This is that the inverse of a function f exists if f is injective only. So this is not. Why? Because you can take any injective function, but it is not surjective. So just take this example: 1, 2, and over here we have 1, 2, 3. So 1 is mapping to 1 and 2 is mapping to 3. So this is our function f. So that f is an injective function. But can we find inverse function? So this is an injection. But can we find inverse function defined from this B to A, namely G? Still, we cannot find such a function. Why? Because that G function over here will not be defined for this element A. So this is not the inverse inverse of a function exists. So we cannot necessarily say that the inverse of a function exists if it is only integer. In problem 2, we have given two relations. We are given a relation R such that if R is a relation and A here is in R if A divides. Basically, the relation we have seen in problem 1. What is set of integers excluding 1? So we exclude 1 and leave all the integers. The minimum element of the given process is. So now we have to find all the minimal elements. So first of all, instead of taking all the z plus, so let us consider only the first 11 or elements. Okay. So that means let's consider this elements. Sorry, we have to exclude 1. So we have 2, 3, 4, up to let's say 12. And then we'll see what happens to the rest of the elements. So let's start with this first 12 elements. So first of all, 2 is there, 3 is not divisible by 2, 4 is divisible by 2, so we will have a diagram like this. 5 is not divisible by 2, 3 or 4. 6 is divisible by both 2 and 3. 7 is divisible by none of them. 8 is divisible by 4. 9 is divisible by 3. 10 is divisible by 5 and 2. 11 is divisible by none of them. And 12 is divisible by 6 and 4. Well, okay, so this is the diagram for first 12 elements. And from this first 12 elements, and then we can just keep on adding 15 like this. So if we add 15 over here, then this will be divisible by 3 and 4 over here. And if we add 13, sorry, so we have to first add 13, then 14 would be like this, that 14 is divisible by 7 and then there is 50 like this. So you can keep on adding elements like this. Now, after computing this for the first 15 elements, so let's say this is point 15. So from the first basic diagram of this first 15 elements, what we can see is that the set of all minimal elements are nothing but this: 2, 3, 5, 7, 11, 13. So basically all the prime numbers. All of these prime numbers are basically the minimal elements. So since we know that the prime numbers only have two divisors, the prime number itself and 1. And since we have already excluded 1, so there is no divisors which is basically distinct from this element also. So now, if we consider the first statement, it says that set of elements 2, 3, 5, 7, 9. So these are the minimal elements. But this is not, since we have seen here that 9 indeed have a divisor 3. So 9 is definitely not a minimal element. And 2 is one of the minimal elements, which is true because we see that the minimal elements are basically all the primes, and 2 is one of them. So 2 is definitely one of the minimal elements. The third statement is that the set of all odd numbers 3, 5, 7, 9, these are the minimal elements. But as you can see that these odd numbers like 9, 15, these are odd numbers, but here these are not minimal numbers. These are divisible by 3, 5, etc. So the set of odd numbers is definitely not the minimal numbers. And definitely, since we have seen that this statement B is true, so B is definitely not true. So in problem 3, we have the number of distinct equivalence classes based on the relation which is given us like this. So AB is related whenever A is congruent to B mod. So this is an equivalence relation. You can check that because A is always congruent to A mod B given any prime integer. So this is always true. So that means this proves the reflexive relation. Also, if we want to prove the symmetric relation, then we can say that A is congruent to B mod B, and that will imply that B is also congruent to A mod B. By the way, when we say that A is congruent to B mod C, so that means that A minus B, C B, this is divisible by C. So C divides this A minus B. So this is what we mean by this statement, A congruent to B mod C. Now, if we consider this A congruent to A mod B, so that means that A minus A, this is always divisible by any integer B, since this is 0. So therefore, we can say that A congruent to A mod for any A. And similarly, if we say that this is true, that A is congruent to B mod B, so that means that E divides A minus B. So that will also mean that E divides minus 1 of B minus A. From here we can write this. Now, if B divides an integer k, then B also divides an integer minus k. This sign minus or plus, this doesn't affect the divisibility of this integer k. We can say that B also divides this integer B minus a, and that will imply that B is also congruent. So symmetric relation is also so reflexive and symmetric, these are true. And what about the transitive property? Now consider that we have two pairs AB and BC. AB which is in the relation R and BC which is also in the relation R. So AB is in the relation R, that means that A congruent to B mod B, and B is also congruent to C mod B. So this means that B minus A is divisible by B. And this means the C minus B, this is divisible by B. So we can write this B minus A as a multiple of B for some integer k. And over here we can write the C minus B is also a multiple of P for some integer, say n. So now we can write that C minus A. So basically we are adding this to together. That is this. So that is that the C minus A is also a C minus A is also divisible by P. So P divides C minus A. This will imply that A is congruent to C. So indeed this relation R that was given to us, this relation is an equivalence relation, and it creates an equivalence classes. So basically all the elements that are related to A should be in the class of A. All the elements that are related to B should be in class of B, and so on. So now consider if we say that A is related to 0 mod. Okay. So if we consider this, that all those integers that are related to 0. So if A is related to 0, then definitely A is congruent to 0 mod. So so we now list down all of those integers. So basically this will imply that B divides A, and this will imply that A will be of this form: 0, P, 2P, 3P, and so on. So these are all those integers that belongs to this class of 0. we can also find this class of 1 mod, because 1 does not belong to this class. So definitely there must be another class, A1 mod B, something like this. I mean, there must exist a class corresponding to this unit 1. And if we consider A is in this class, so then A must be component to 1 mod. And that means that E divides A minus 1. And that will imply that A is of the form E plus, sorry, 1, E plus 1, E plus 2P plus 1, and so on. So these are all the elements that belongs to this class 1. And similarly, we can go up to this class P minus 1. 1. So we consider this class, then that will mean that P divides this A minus B plus 1. And this will imply that A is of the form P plus 1, sorry, A is of the form P minus 1, 2P minus 1, 3P minus 1, and so on. So these are all the classes that we can find for any integer. Now, indeed, even if we have given this p as a prime integer, but this is not really necessary. This condition for prime integer, this is not really needed, because for any integer, this class that we are seeing over here, this will only give us p many classes. 0 for the class of 0, class of 1, and the class of p minus 1. So there are total p many distinct classes. In problem 4, we are given two relations, namely the relation R1, which says that A and B two sets are related whenever A intersection B is equals to B. And R2 is a relation which says that A and B are related whenever A is a subset of B. So now, which of the now we have to figure out if these statements A, B, C, or D, these are true or not. So the first statement says that R1 intersection, that means this relation over here, if this is a coset or not, and R2 is a equivalence relation or not. So basically we have to figure out whether this R1 and R2, these are coset or equivalence relation for each one of them. Now to do that, so basically we have this R1 and R2, and we have to figure out whether this is a coset or equivalence relation. Now for coset, in order to be a coset, what are the conditions for relation? The first condition is the reflexive. Second is antisymmetric. And the third one is transitive. On the other hand, for equivalence relation, we need reflexive, symmetric, and transitive. These are the conditions that are needed to be fulfilled. So for R1, we will say that we will now check whether this is reflexive, antisymmetric, symmetric, or transitive. We will check all these cases for R1 and R2. Now consider, first of all, let's consider the reflexive relation. So for reflexive relation, the R1 was that was this, all those AB such that A intersection B is equal to, and R2 was that all those AB such that A is a subset of B. Now, what about the reflexive relation? So consider any arbitrary set A. Now A intersection A is indeed A, so we have to imply that A this belongs to this R1, this relation, and again A is a subset of A. You don't have to do this. Right? So that will imply that AA is also belongs to R2. So definitely R1 and R2 both are reflexive. So both of them are reflexive relations. Now what about antisymmetric? Now what was the antisymmetric relation? That if AB for any AB, if AB belongs to R1, sorry, for any relation R, if AB belongs to R and BA belongs to R, so that will imply that A is equal to B. So now let's see whether R1 and R2 both are antisymmetric or not. Now for R1, we consider again two sets A and B such that AB belongs to R1 and BA belongs to R1. So what does that mean? So AB belongs to R1 means that A intersection B is equal to B, and similarly B intersection R1, that means that B intersection A is equals to A. Now A intersection B is equals to B intersection A. So from there we can conclude that A is equal to B. So that means that R1 is definitely antisymmetric. And what about R2? So for R2 again, we can consider this AB belongs to R2 and BA belongs to R2. Both of these pairs belongs to R2. Now AB belongs to R2, that means that A is a subset of B, and BA is in R2, that means that B is a subset of A. And we consider these two statements, A is a subset of B and B is a subset of A. So that implies only that A is equal to B. So that means that this relation R2 is also antisymmetric. Now what about the symmetric property? Now we know that if two elements, if one relation cannot be simultaneously symmetric and antisymmetric, we know that. But still, let's see that we can prove that. We can check the symmetric condition. So for symmetric, we need to have that if AB belongs to R, for any relation R, if AB belongs to this relation, that will imply that BA also belongs to the relation R. So now consider the relation R1. So in the R1 relation, we consider that AB belongs to this R1 relation. So that means A intersection B is equal to B. We have this. Now from there we have to prove that A intersection B intersection A is equal to A. That is, in order to prove that BA belongs to R1, we have to prove that B intersection A is equal to A. But we can prove that this is actually not. So we just can take an example. So the example is very simple. We take 1, 2, 3 as A, and B is basically a singleton set. Let's say 1. So if we take A intersection B, then A intersection B would nothing but equal to this singleton set 1, which is B. But again, B intersection A is not equal to A, because B intersection A would actually be equal to this singleton 1, and that is definitely not equal to A. So we have an example for which this is definitely not. So this R1 is definitely not symmetric relation. And similarly, we can also say that this is not antisymmetric. Sorry, this relation R2 is also not an antisymmetric. Sorry, R2 is not a symmetric relation. Why? Because we can take the same example. So for this, we can say that B is a subset of, okay, not the same example. So let us consider this as this. We can take A to be singleton 1 and B to be, let's say, 1. Then we can definitely say that A is a subset of B, meaning that A is related. But if we consider BA, this no longer belongs to this relation R because B is definitely not a subset of. Okay. So therefore, this relation over here this relation R2 is not a sorry. This relation R2 is not a symmetric relation and not the R1. So R1 and R2 both are not symmetric relation. Finally, we have to prove the transitivity property. For transitive property, what we have to assume is that AB belongs to R1. So for R1, we have to assume that this AB belongs to R1 and BC belongs to R1. And this A, B, C are all arbitrary sets. Then from there, we have to prove that AC also belongs to R1. This is what we have to prove. Now, AB belongs to R1 means that A intersection B is equal to B, and BC belongs to R1 means that B intersection C is equal to C. What can we say about A intersection C? Now, since A intersection B is equal to B, okay, so basically we have to prove that this A intersection C is equal to C. So there are two ways to do that. I mean, one way is obvious because A intersection C is a subset of C. That one is obvious. But we have to prove the other way. That is, we have to C is a subset of A intersection C. Now, how can we do that? So we can just select an arbitrary element. Say X be an arbitrary element that is in set C. Okay. Now, if X is in C, so and also we have that C is equals to B intersection C. So this will imply that X belongs to B and X belongs to C. So basically this implies that X belongs to B. X belongs to B intersection C means that X belongs to B and X belongs to C. So we don't need X belongs to C, we just need this X belongs to B over here. Now this X belongs to B, this means that B is again is equal to A intersection B. So we can say that X belongs to A and X belongs to B. Why? Because B is equals to A intersection B. So from there we can conclude that this X is indeed in A. Okay. And we don't need this X belongs to A is an X belongs to B. Now we already had that X is in C, and now from there we have put that X is in B. So using both of this, we can say that X definitely belongs to A intersection C. So we started with an arbitrary element X which is in C, and we end up with X in A intersection C. So we can say that C is indeed a subset of A intersection C, meaning that C is equals to A intersection C. So the relation R1 is definitely a transitive relation because we have proved that this AC belongs to R1. So this is a transitive relation. Now what about R2? For R2, again we assume that there are two AB pairs in R2 and BC. AB pair and this pair BC. These are both in R2. And that means that A is a subset of B. From A, B belongs to R2. We can conclude that A is a subset of B. And from here, we can conclude that B is a subset of C. So this is obvious that A is a subset of B and B is also a subset of C. So that should imply that A is a subset of C. And if A is a subset of C, so that means that AC also belongs to this relation R2. So it is easy to see that this R2 relation is indeed a transitive relation. And also, as you can see earlier, that both R1 and R2 are reflexive and asymmetric and transitive. That means that both of them have cosets. So this is a coset and this is also a coset. And none of them are equivalent relation. So the first question, the first statement was that R1 is a coset and R2 is an equivalence relation. This is not true. Both R1 and R2 are equivalence relations. This is also not true. R1 is an equivalence relation and R2 is a coset. This is also not true. But the final so the answer should be that both R1 and R2 they are cosets. Okay. So now we have some in problem 5. What we have here is that we have a function f. Sorry, we have a set of function f. We have a set of function f, and we say that this function and this n0 is taken as this set of all natural numbers, including the 0. And we are considering this O to be a relation over this function f. And we say that this fg pair is in the relation O whenever we say that this condition holds, that is 0 less than fn plus equals to cgn, where c is a constant term, and there exists a n0 such that this is true for all n greater than equals to n0. Okay. So now we have to see whether this relation okay. Oh, sorry about this. This is the same thing that I have copied from the previous. This should be. So basically, we have to choose the correct statement for this relation. Forget about this. Okay. So the relation. So this first question is the relation is a partial order. Second is the relation is a total order. Third is the relation is a equivalence relation, and fourth one is the none of the given option is true. We have to choose the incorrect statements. So what was the partial order? So we have seen in the previous question that the partial order means that we need three conditions: reflexive, antisymmetric, and transitive. These three cases, these three properties we need for the partial order. What about total order? So for total order, we need all these conditions for partial orders. That means it has to be a partial order. And an extra condition should be there, which is any two elements or elements must be comparable. What does it mean by any two elements must be comparable? That means if A, B are two elements in the any two arbitrary elements in the set, then either A is related to B or B is related to A. This must be. So Or in some cases, in some books, this is also called the total connectivity of this order. So we need partial ordering. We need for total order, we need this condition, and for equivalence relation, we know that we need three cases, which is three properties, which is reflexive, symmetric, and transitive. So now again, we will check whether this relation that was given to us, whether this is reflexive or not, transitive or not, and symmetric or not, anti-symmetric or not, and finally transitive or not. Or rather, we just have to see that whether it's a partial order or equivalence relation or not. So first, let's check the reflexive relation. Now, if we are given any function in the set of all functions, okay, so then what we can say about this is that 0 is less than, sorry, okay, so this is a function from 0 to r plus, and r plus is basically the set of all positive integers. So definitely this function, so for all these all the values at n, we will definitely have uh, if n greater than 0 for n. And also we can see that this is nothing but equals to f of for all. This is true since these functions are basically set of all functions if mapping from n0 to 1 plus. Since this is a set of all functions, we can definitely write this. And this condition, and for here, the c, the constant c is nothing but the constant 1. And therefore, we can say that this function, sorry, this PRFF, this definitely belongs to this relation. Okay. So definitely, this relation O is symmetric. Sorry, this is reflexive. So what about the symmetric relation? So what about the symmetric relation? So in the symmetric relation, we have so basically we have to prove that this is actually not symmetric. Okay. We can prove this. How can we do that? We can just have some if, sorry, we need to find if G, which belongs to this order, but GF does not belongs to this order. So consider this function. So consider if n to be the function n square and Gn to be the function n. Okay. Now, if we consider this, if n minus of Cj, so where C is a constant, so we don't know which constant this is, but let's say the C is some constant. Okay, so this function is nothing but n square minus C. Now, if you consider, now definitely we can for any, I mean, if we have a constant like this, then we can definitely find some n0 such that for any n0, so we can write that you can find some n0 such that for all n greater than n0 or greater or equals to n0, we can have that this n square minus cn is greater than 0. Only if we take n0 to be the number uh, c. So let's say that this n0 is equal to c. C's are whether I mean the c can be any constant, so it can be even a real number. So let's say that n0 is not c, but rather it's a number which is less than c. It's the smallest possible integer which is less than c. So if we take that as n0, then for that number, this n square minus c will definitely be greater than 0. And if we take any integer larger than that, that will also be greater than 0. Why? So if we write the graph, draw the graph, then that will make it clear. So basically, this is the graph for y is equals to x square, and this is the graph for y is equals to x. So this is our fn, and this is our gn. So if you take in n0 over here, then we can say that for all n greater than equals to n0, we can say that fn is less equals to gn. Forget about this c. So basically, for some n, there exists some n0 for which you can write this, and 0 is greater than fn. That is also good. So you can write this. So therefore, we can say that this f and g is definitely in this relation form. But what about gf? Now that is the point. Now if we try to figure out this one, we have fn is equals to n square and gn is equals to n. Then consider this gn minus cfn for any constants. So that should be like n minus cn square, and c is a constant. Now, can we say that this always greater than 0 for some uh, for all n greater than n0, where n0 is some integer? Can we always say that? Because now, uh, this is nothing but n into 1 minus cn. Now, n will always be positive, but as n increases, it doesn't matter what we take as this constant c. As since this is a constant, then but there will be some very large integer n for which this term 1 minus cn, this will be negative, and therefore this term will definitely be negative. That means this will be less than 0. That is, we can have this gn is actually less than cf. Sorry. Uh, Basically, we want to cannot be. So over here, fx is in gn. Sorry, fx is less than gn. That's true. But fx cannot be less than gn. So we will need to show that this is not possible. This is not possible. And in order to do that, we have to show that this fx, sorry, cgx minus of fx, this has to be positive. If this is true, then this has to be positive. And from there, we can say that this cn minus n square, this has to be positive. For very large, for n greater than or equals to some n, for all n. So that means that c minus n multiplied by n, this is always greater than 0. Now, if when n is greater than c, whenever n is greater than c, is constant c, then this term will always be negative 0. So this is not true. Since we are saying that this has to be true for all n greater than equals to n0, and as you can see, for c, for any n which is greater than c, this term will always be negative. So this is not possible for all n greater than equals to n0. So that means that for this example, we cannot have like gf belongs to O. So this is not possible. So this is definitely not a symmetric relation. What about the antisymmetry? Antisymmetry says that if fx if g this belongs to the relation O, gf also belongs to the relation O, then we must have that f is equal to g. Now we can actually give you an example. We can say that if x is nothing but equals to, sorry, if n is nothing but equals to n, is defined by this function, and gx is defined by, sorry, gn is defined by 2n. Then we can see that if n is definitely less than equals to 2, sorry, definitely less than equals to gn for all n greater than 0. Sorry, yes, for all n greater than 0. So this is true. So that means that this is true for this example, f and g. And similarly, we can write that this gn is less than equals to twice of f for all n greater than g equal to 0. So gf is also is in this relation O. So f and g both belongs to this relation O, but this f is equals to g. As we can see here that f and g are defined as a and 2. So f is definitely not equal to g. So this is also not an antisymmetric relation. Now, since we have already proved that this is not a reflexive relation, not a symmetric relation, then there is no way that this can be an equivalence relation. We have also proved that this is not a reflexive, this is a reflexive relation, but it is not an antisymmetric relation. And definitely that is not partial order. And since it is not a partial order, so this cannot even be a total order. So we don't have to really check the transitivity property, but if you want, then you can also check that. And this definitely is, oh, sorry. Oh, so the question was to select all the incorrect statements. So this is definitely incorrect, and these are correct. Okay. So now, from here we will start some of the problems based on cardinality of sets. So now over here we have given two sets 0, 1 and this closed interval 0, 1. Now we have to show that these two have same cardinality. So basically we have to find a bijective mapping. So we know the one theorem that if we can find a injective mapping from 0, 1 to this closed interval 0, 1, and also a bijective mapping from this closed interval 0, 1 to open interval 0, 1. Sorry, not bijective, but injective mapping. So if both if G are injective, then we can say that there exists a bijection. So basically, we now have to find two injective maps, F and G. So how can we find that? So first of all, we have. So basically, first we will try to find this open interval 0, 1 to 0, 1. So this map is very easy. So basically, we take the mapping from this to this as fx is equal to x, the identity map. then this identity map is definitely injective map. This is not a surjective map because for 0 and 1, since 0 and 1 elements are not in this set, for 0 and 1 in the codomain set, we don't have any element. But for any other sets, we have that element, sorry, this map is exactly assigns that particular element X in the domain set. So this is an injective map. Now, what about this map G from 0, 1 to 0, 1? So for this map, what we can do is that we have something like this. So we have 0 over here and 1 over here. And we can find a line like this. Okay. So consider this map. So if we take any x, so this x should be x plus 4 and 2. Or so x plus 2 by 4. X by 2 plus 1. So if you take this, let's take this, as you can see that for G0, this will map to half plus 1. So this will map to 1. And for Z1, this will map to uh, half plus 1. So if we consider this height to be 1 4, and if we consider this height to be our half plus 1 4, then definitely this is our map G, and this is an injective map. You can check that this is an injective map. So definitely we have the injective map from 0 1 0 1 sorry, open interval 0 1 to close interval 0 1, and similarly we have a injective map from close interval 0 1 to open interval 0 1. Then definitely we have a bijection from 0 1 to this close interval 0 1. Now let's solve problem 7. So problem 7, we have to show that there is no infinite set A where this cardinality of A is less than alpha. That means if A is an infinite set, then we cannot have this. We at least have to have this. This is the least. We at least have to have the cardinality of A is equal to alpha. We cannot have some infinity which is less than alpha. So now we will prove two claims. So the first claim is that if A is a, so for any A with cardinality of A less than the cardinality of the natural numbers, so this equals to the cardinality of natural number, then there exists a subset B of n such that the cardinality of A is equals to the cardinality of A. So this is our claim 1, and the claim 2 is that for any subset B of n, so for any subset, rather any subset B of this natural number set n, either B is finite or countably infinite. That means that B is countable. So B is either finite or countably infinite, means that B has to be countable. So now let us first prove these two claims. So over here, as you can see, is that this cardinality of A is less than I. This is what we are given. We are considering this. We are considering this to be true, and then we will show that we have arrived at a contradiction. So we have this. We have this over here. So if we do have over here, if we do have this over here, then we can say that. Oh, sorry. So first, basically, we have to put these two claims. Then we will put the theorem. Okay. So the first claim is that we for any set A with this. So basically, we are considering this arbitrary set A that has this, which is so if this is true, then we can say that there exists a surjection. So there is an injective mapping from A to N. Since there are less elements in A, so we can say that, or at most the same element as N. So then we can say that there always exists an injective map from A to N. So now consider this is our map from A to N. So it is a mapping from maps from A to N, and this is a injective mapping. Now consider f of A. So this f of A is nothing but the this is nothing but all those f A such that A belongs to A. So this is called the image set. Image setup. So instead of writing this as if A, we can also write it as an image set of F. Now, F of A, all these elements are basically mapping to the natural number set. So definitely we can say that this F A is nothing but a subset of N. So this image set is basically a subset of N. Now, consider this B. And if we consider this map F from A to B, it was a map defined from A to N definitely. But if we restrict that codomain set to B, then we can say that all for any element in B, there is always a image. Sorry, there is always a element assigned in the set A, such that f of A will be equal to B. We can always say that. So that is this is a injective as well as and bijective. Sorry, injective and surjective. Meaning that this is a bijective. This is a bijection. So since we can find a bijection from A to B, where B is a subset of N, then we can write that the cardinality of A is equally equal to cardinality of B. So the first way is true. That means if we have any set with this property, then we must have this A is equal to B. And what about this claim? The second claim is that if we have any subset B of N, then either B is finite or it is non-trivially infinite. So we do not consider the case where B is finite. I mean, B can be finite, or if B is finite. So consider that B is infinite. Now, B is a subset of it. Sorry, B is a subset of it. Then we can have, so consider this N to be 1, 2, 3, and so on. So we have this 1, 2, 3, 4, so on. Now consider all the elements of in B. So B, now since B is a subset of this natural number set, then we can now start labeling B. How? So suppose that 4 belongs to B, then we can first label, and 4 is the first element that appeared in this enumeration of N. Then we can label 4 as 1. and let's say that there is some B over here. Okay. So B1 over here. That was the second element in B. Then we can just label it as 2 and so on. So B2 is 3 and so on. So we keep the ordering of the elements in B and we label them in this way. So basically, we can enumerate the elements of B in the same way. So B also must be countable. That is, the cardinality of B is unknown. Now from there we can now prove this one. Now if we say that A is a infinite set such that the cardinality of A is less than alpha, if we say that this is true, and we will arrive at a contradiction. If this is true, then from the claim 1, we can say that there exists a subset B such that the cardinality of A is equal to cardinality of B. So there exists a B subset of A such that cardinality of A is equal to cardinality of B. Now from claim 2, we can say that since B is a subset of N, then B is either finite or countably infinite. So P is definitely not finite. Why? Because we have assumed that A is an infinite set. And if B is finite, then cardinality of B equals to cardinality of A. This implies that A is finite, and that is not possible. So we can say that this is not finite. B is not finite. So if B is not finite, then we can say that the cardinality of B is alpha, and that is nothing but equal to the cardinality of A. So this is a contradiction. So our assumption was wrong. That is, this is not true. So now, next question is that given any infinite set, it contains countable infinite subset. So this is a very easy proof. So if we consider A to be an infinite set, now we don't know if it is countable or uncountable, but we know that it is an infinite set. Now what we can do here is that we know that this is an infinite set, then A1 belongs to A. There exists some A1 that belongs to the set A. Okay. So now we take the set P as A1. Okay. And take the set A, or rather say take the set A1 as A minus this set A1. Next, what we do is that this A1 is now we have taken only one element, taken out only one element from this set A, which is an infinite set. So therefore, this A1 is again an infinite set. So since A1 is an infinite set, so we can select the A2 from A1 and then update P as A1 and update and take A2 as A minus A1. Now we are only so at each step. So even at the nth step, so we keep on doing this up to nth step. So at nth step, what we do is that we select this an from an minus 1. We update P as a1, a2 up to an, and we take an to be a minus a1, a2 up to an. Now for any n, this set a1 equal to an, this is a finite set. And if we take out finite to many elements from our infinite set, then this A would still be an infinite set. And therefore, we can keep on sampling points from this set, from the set A. And therefore, we can ultimately say, okay, so we can just say this to be P1, P2, and Pn like this. And we can select this set T to be the union of all Ds. these TIs, these are all finite sets, and we have already proved in the we have seen the proof in the lectures that if TIs are uncountable, sorry, if TIs are countable sets, then their unions, I mean unions of countably many countable sets, that is again a countable set. So this is a so these all these TIs are basically finite sets. So they are countable sets, and we are taking the union over all these i's, and then so therefore P again is a countable set, countably infinite set. So we can so basically this what you can say here is that this T over here is a countable infinite subset of this set A over here. Okay, so now we have to prove over here that union of countable number of countable sets is countable. Okay, sorry. So basically, we should have proved this first and then come to this problem over here. So now we have to prove this. That so suppose that we have countably many countable sets. So let us consider S1, S2, S3. These are all countable sets. Now we take the countable units. That is, we are just taking these units. Countable, countable in infinite sets. We are just taking the union of them all. Now we have to prove that this S is again a countable set. So basically, we have to find the find the proper sequencing of all these elements in S1, S2, S3, and all. So first of all, what we do is that we first enumerate all the since S1, S2, S3, these are all countable sets. We can enumerate those elements. That means that we can write it in this way. So suppose that all the elements can be written as this: S11, S12, S13, and so on. Similarly, for this one, we can write S21, 22, 23, and so on. S31, S32, S33, and so on. And over here we have this is some Sn, which is Sn1, Sn2, Sn3, and so on. Now, how can we label? So, if we take the union of all these elements, then how can we label them? The process of labeling is in this way. So, we start in this diagonal, and then we go for this diagonal over here. And we write down all these elements in this diagonal, and so on. Now, you can see that all of the elements is so if we take any SI, sorry, if we take any elements, let's say this is 32, or rather, we can just say if we take any SIZ, okay, so that means that that belongs to this SI. One element, such element, which is in the jth column and ith. Okay. So we can even find our one diagonal for which for which this Sij belongs on that diagonal. And once we have used this, find out these diagonals, we can now enumerate them in this way. Here first we take this one, then we take this 1, 2, and 2, 1, this 2, 1, then is 1, 3, is 2, 2, is 3, 1, 1, 3, 2, 2, and 3, 1. and so on. You can enumerate all the elements of S in this way. So this is exactly same as saying that first we enumerate all the elements such that the I plus j is equals to 1, and for this I plus j is equals to 2, and I plus j is equals to 3, and so on. So basically we are taking these diagonals. So all the elements of S can be enumerated in this way. So therefore we can say that S is countable. Now we have to find some examples of two countable sets A and B such that their intersection is finite, countable, infinite, and uncountable. So suppose we are taking two countable sets, which is 1, 2, like this, which is basically the closed interval 1, and B is closed interval 2. And we take the intersection of them together. So as we can see, it is so that set A is basically 1 to 2, point 2 over here, and this set B would be from point 2 to point 3. All the elements will be different. So the only point that is that belongs in the intersection is this one. So A intersection B would be equal to a singleton group, which is a finite set. The second option, the second one was that A is equal to the countable infinite, the intersection countable infinite. Okay, so we can take A to be Z union 2, 3, this open interval 2, 3, and B is basically Z union this open interval 3, 4. Okay. So now in this case, what we would have here is that the set A would be all the integer points like these are all -1, 0, 1, 2, 3, 4, 5, 6, 7, and something like that. And A set is all these points, all these integer points, and 2, 3, all the elements in between 2 and 3. And B set is basically all these points and the element between 3 and 4. So if we take the intersection of these two sets, then we will only find these integer points, because these two areas doesn't have anything common. These two open intervals doesn't have any common elements. Therefore, the intersection of these two sets will only be equal to the set Z, which is definitely countable set, infinite set. Now, third one, we have to find an uncountable set. Okay, so let's say that we are taking a okay, so we can just take this set A. Consider this set A as Z union 2, 3, and B is also the same set Z union 2, 3. So basically A intersection B would be Z union 2, 3. Now, what is this set? So this set would be like this: -1, 0, 1, 2, 3, 4, and so on, and all the elements in between 2 and 3. So these are all the points. These are all the points that belongs to A intersection B. So A intersection B. And this is definitely a countable set. Sorry, uncountable set, because these elements from 2 to 3, these are uncountable. Okay. So now look at the problem 11. So this is the last problem. So in this problem we have two cases. The first set, two sets are given. So first set is given by all those integers that are divisible by 5 but not 7. So what are the integers that are divisible by 5? So basically first we will list down all those integers that are divisible by 5. So that will be 0, plus minus 5, plus minus 10, plus minus 15, and plus minus 35, plus minus 40, and so on. Now we need to figure out all those elements that are not divisible. From this list, we have to exclude all those elements that are divisible by 7. So those are 35 and all possible multiples of 35. Yes. So all possible multiples of 35 that should also be deleted from this list. So even though we delete all those elements from this list, then we will have this list over here. So this is a list of all those integers that are divisible by 5 but not 7. So now we can just enumerate all these elements in this way. 0, then plus 30, then 5 minus 5, 10 minus 10, 15 minus 15, and so on. So we can basically enumerate all these elements in this way, so that this integer divisible by 5 but not 7, this is a countable set. Now, secondly, we have this real numbers whose decimal representation consists of all the ones. So now, first of all, we will so this real numbers with decimal representation consists of all ones. So now, the decimal representation that consists of all ones would be of this form. So there might be some k many ones and m many ones over there. Right. So it can be of this form. And it might not be finite. There can be arbitrarily large number of elements or arbitrarily large number of large number of digits after this decimal. This may not be finite. It might be arbitrarily large. So now, what we can do is that we can find these sets. So first of all, I will take the set S0. So we define the set S0 as all those elements that are basically consist of all this decimal representation of numbers that consist only ones, and before the decimal there is no number. So basically there is nothing over here, but we only have this like this 1.11, 1.111, and so on. And as you can see that these are all countable elements. Sorry, these are this set. This is 0 set. This is a countable set. We can also consider this S1 set, which says that before decimal there is only 1, and after that, similarly, we will have like this 1.11, 1.111, and so on. So similarly, we can just have Sn like this, where Sn does have n many ones before the decimals. Then we have the decimal number 1.1. Again, we have this n many ones before decimal, then 1, and so on. Now, definitely this S0, S1, Sn, all these are countable sets. Each SIs are countable. And what we have given is that the real numbers whose discrete representation consist of all ones. This is nothing but the set S, which is basically the union of all SIs from I is equals to 1 to 8. Okay, so this is the set that we are considering over here, and this is basically countable union of countable unions of uh, countable sets. So these are all SIs are all countable sets, and we are taking the countable union. So S is also countable. And therefore we can conclude that this is indeed a countable set. Thank you. This is the end of today's live session. So if you have any questions, you can ask me, or this is the end of this session. We can meet next week.